Hi, I am William Tarneberg from Lund University. Welcome and thanks for taking your time to learn about our collaborative efforts in this Vinnova-funded project that brings together Ericsson, RISE, Lund University, Volvo Construction Equipment, Alkit, TCN, and Epiroc, as well as many other partners, to drive the advancements in 5G technology. So our goal is to advance 5G technology by addressing its crucial challenges in realizing mission-critical applications, by improving network reliability and supporting these crucial applications in a cross-layer manner. Now, these steps are key for developing telecommunications both now and in the future. Let's take a look at some of those achievements. We made key AI advancements for network management, ensuring robust operations of wireless networks. Our team has also improved performance for crucial services such as controllers that run over the cloud, ensuring that they run seamlessly and they're able to adapt to variations in the networks. We've also enhanced user satisfaction through better quality of experience measurements and experiments. In transportation, the team has enabled signaling from vehicles to span multiple vehicles and created advancements in those kind of platforms. Our efforts in total have yielded 24 publications, 3 licentiate degrees, supervised 4 degree projects, and have contributed to standards shaping the future of this technology. So, join me to explore these achievements in more detail in the coming slides. At the heart of our mission lies the exploration of 5G's pivotal role in supporting industrial applications, from enabling remote control vehicles to ensuring mission-critical applications run flawlessly. The quest for optimizing end-to-end performance is crucial, and you'll see this throughout. Managing 5G networks presents unique challenges. As shown in the figure to your right, the dynamic challenges and configurations within the network can lead to performance degradation. This box diagram illustrates our architectural approach to identifying root causes for application-driven mitigation actions. Our focus on delay prediction and characterization, informed by base station statistics, represents a significant effort towards addressing these complexities. Now, in this innovative landscape, we harness the power of AI with advanced methods like CDANN, which stands for Custom Domain Adversarial Neural Networks, for enhanced networks performance modeling. CDANN represents a tailored approach in the domain adversarial neural network family, designed for semi-supervised learning. It excels in scenarios with both abundant and scarce label data. The ROC-AUC graph shown here, it stands for Receiver Operating Characteristics, Area Under Curve, is a testament to CDANN's robustness. It's a crucial measure for classifier performance, where a higher area under the curve signifies better model discrimination. As you can observe, the CDAN model maintains superior performance across different levels of labeled data, ensuring efficient adaptation to network changes and mitigating the high costs traditionally associated with data labeling. Now, into our work on quality of experience. Our journey begins with an exploration of how network performance impacts the quality of experience for users, emphasizing the necessity for precision and control in our testing methodologies. Following this, we'll unveil the intricacies of developing a cutting-edge lab platform designed for remote control experiments, showcasing the pivotal role of technology in enhancing user interaction. Lastly, we'll delve into the innovative applications of computer vision in industrial settings, highlighting the potential to revolutionize fault detection and the reduction of and reliance on human judgment. Right. So quality of experience, or QoE, where we have a special focus on how it's affected by varying network performances. Our methodical approach includes crafting a meticulous plan for conducting field tests within a rigorously controlled environment, ensuring the integrity and relevance of our data. We meticulously choose our test tracks and tasks to align with our study's objectives. To comprehensively understand the impact, we introduced variations in latency conditions. This step is pivotal in uncovering the nuances of qualitative experiences, aiming to enhance user experiences by identifying optimal network parameters. Our project harnesses the NVIDIA Jetson Nano platform to facilitate a controlled, remote exploitation platform. The incorporation of GStream allows for effective video streaming with less than 140 milliseconds of latency, essential for the precision required in our work. We've undertaken a detailed examination of key parameters such as field of view, video quality, latency, and display type to optimize our remote controlled experiments. Through these efforts, and with the collaboration of 20 participants, we've managed not to only conduct but refine our approach to achieve interactive and responsive control in a hands-on research environment. As we delve deeper into the transformative field of computer vision, our initiative is to redefine the standard for fault detection in drill bits. We leverage not only YOLO version 5, but also the next leap in object detection technology, YOLO version 8. These advancements in models epitomize the pinnacle of our efforts to swiftly and precisely detect and track faults in real time. Our motivation is twofold: to bring intelligence to automatic failure detection and to refine the necessity for specialized technicians. This transition seeks to eradicate human errors and establish a new norm in technical precision. The methodology we've adopted is as comprehensive as it is precise. By developing a tailored computer vision tool that benefits from the advancements in YOLO version 5 and version 8, we set out to accurately localize and classify faults. Our development process is rigorous, starting from dataset preparation, moving through the intricate phases of model training, and accumulating in the critical phase of inference. This meticulous process is not just about employing cutting-edge technology, it's about reimagining and enhancing the detection of faults. Now, Alkit and TCN has been instrumental in developing use cases for connected vehicles. By engineering sophisticated components for data collection and designing simulation tools for vehicle-to-vehicle communication, they have pioneered techniques for transmitting vehicles' internal signals. Overview here paints a comprehensive picture of the advanced vehicular technologies developed by Alkit and TCN, integral to the modernization of transportation. Now, this project, we've enhanced Alkit's WISE vehicle data analysis platform, offering a more granular insight and optimizing vehicle performance through advanced analytics. We also developed further TCN's time analysis as a specialized tool for the precise evaluation of time-critical data, a cornerstone in the efficacy of autonomous decision-making in real-time scenarios. We now delve into Lund University's contributions that range from innovative scheduling algorithms for cloud computing systems to fundamental work on age of information as well as security. Our research introduces two innovative strategies for cloud performance optimization: adaptive out-of-phase scheduling that minimizes request overlap, effectively reducing queuing times. Here, a PID controller adjusts timing based on server feedback, and that enhances resource distribution and spreads it out over time. As you can see in the figure to the top right, the left-hand side of it shows 10 different clients sending requests to a service periodically. So the y-axis represents the 10 different clients, and the x-axis represents time. And in that time span, there are 3 different periods. The blue bars represents the duration of time a request spends in the system. So the longer the bars, the longer the time the system a request spends in the system. So as you can see, a lot of the requests overlap in time. What we desire and what we've achieved is what you see on the right-hand side of the figure. Here, requests are dispersed in time within each period, so that they arrive at different times in that period, and thus the bars are shorter, representing that they spend less time in the system. So our results show that we have halved the execution time, halved the response time of the system, and thus also almost eliminating the variance in the system. Now, in parallel, we've also developed the punctual cloud framework that guarantees the prompt delivery of control signals, critical for time-sensitive processes, even amidst very high network delays. As illustrated in the lower figure, it harnesses basic controllers for dynamic processes management and employs a microservice architecture for flexible deployment. So what it does is it makes sure that control messages are delivered promptly, or that the correct information is delivered promptly. So in a system with so that is subject to large delays, messages will of course be delivered, information will be old and stale and no longer useful, as you can see in the orange line in the figure, where punctuality on the y-axis is the currentness or the freshness of that data, the punctuality of that data, and on the x-axis we have subjected the system to various degrees of delay. Now, with the punctual cloud framework represented by the blue line, we're able to deliver using prediction and intricate controllers. We're able to maintain a very high level of punctuality in the system, which is crucial for these kind of control systems. Now, both of these approaches have been developed and tested using real cloud systems and real processes. Now, in addition, our latest security framework fortifies cloud-based systems against cyber threats, integrating a robust three-step process for attack handling, detection, isolation, as well as mitigation. This proactive approach has been rigorously tested on real-world models, affirming its practical applicability and effectiveness. Even amidst disruptions, it has proven to provide a quick, stabilizing response, ensuring system integrity. So I'd like you to point you to the figure at the bottom right. Here, the blue bars represent the system under normal circumstances, and the height of the bar represents the amount of error the system is subjected to. So in normal circumstances, the system can be expected to be subject to a small amount of error given variations in the systems and so on. Now, on the x-axis, you'll have different scenarios that we've subjected the system to, different operating scenarios we've subjected it to. The yellow or orange bars represent the system under attack, when an adversary has been manipulating the system and thus subjecting it to error, causing error, which can be detrimental or catastrophic to the system. Now, with our approach, it's able to detect, isolate, and mitigate these adversarial acts, produce an output, an error that is very close to what you would experience under normal circumstances. So this project also saw fruitful international collaboration, such as between Ericsson and Turkcell for 5G energy management, and between RISE and Nokia on quality of experience models. These partnerships have enhanced our project scope and facilitated contribution to global standards. Right. So thank you for paying attention. We appreciate you taking the time to learn about our efforts and achievements in this Vinnova Imminence project. Thank you for paying attention.